Today I'm going to talk about scaling Solr with SolrCloud. We'll start from a bit of history. We'll see how the old architecture worked, how the new architecture works. I'll tell you about some specific features that may help you with scaling. And I'll talk just a few words, I promise, about monitoring. Sorry. Before we start, for those of you who are not familiar with me, allow me to introduce myself. I work at Sematext where I'm a search consultant. I help clients with their search problems, both with Elasticsearch, Solr, and Lucene. I'm also a software engineer working on various projects, like our newest child, Logzine project, the data analysis tool. I'm a co-founder of SolPL, the site where we try to share knowledge about Solr and help people. I'm also a happy husband and a father of 2 great children. Sorry. And I happen to write a few books, 2 about Solr, 2 about Elasticsearch, so that's a background. Let's start from history. I don't know if you're familiar with it, but in 2004, Yoni creates Solr, a proprietary software based on Lucene that's 2 years later donated to Apache Software Foundation and starts its graduation process. After almost a year, there is a graduation from the incubator, and Solr goes under the umbrella of Lucene project. We have a release of Solr 1.3 1 year later, then another year later, Solr 1.4 comes with the new replication, the Java one, which is still used. We got rid of all the scripts. We could now use Solr not only on Linux-based systems or Unix-based, but also on Windows. And it works. Finally, in 2010, the PMC of Solr and Lucene decided to merge those 2 projects into a single one, so that their code base in a single place, they share, and they are more tied together. From that point, Solr didn't have to wait for Lucene to be released in order to incorporate the changes. It was done in parallel. Finally, in 2012, we've got the first release of Solr 4X, the Solr 4.0, which is the first version of having the cloud functionality to all the users. You didn't have to check out the other branch to use the cloud. And in this year, we have 4.1 and counting. Currently, there is 4.5.1, and the incoming release of Solr 4.6. I've seen a mailing list post earlier today that it should be pushed in a few weeks, maybe 2, 3, or maybe a bit more if there are bugs. How it looked all in the past when we wanted to scale Solr. We have to use the master-slave architecture. So let's start from the simplest approach. We had a single master that was designed to index our data. If we wanted to serve queries and we wanted to have not stress out the master to serve the queries, we were to introduce slaves. And our application, which sent data to the master, and then slaves pulled the data out from the master based on the poll interval stored in the Solr config XML. So it was something like this. It worked. For a long time it worked, but there were few issues that people were struggling with when it came to this architecture. First of all, there was a single point of failure, which generally you want to avoid as much as you can. If the master was down, just like this, your data couldn't be updated at all. You had to bring it up, push your data again, and your slaves were only able to serve the view they had before the master failed. It happened. You couldn't have 2 master servers because you would have to reconfigure. You could have, but that imagine that you have to push the data to both masters. You could synchronize them if they are in sync, and you would have to change slave configurations to get the data from the new master and stuff like that. Non-convenient at all. The second thing was the replication time, because slaves were not automatically informed about the data, the newest data on the master. So they had a poll interval defined on which they pulled the data. Imagine a situation like this where you have an indexing application that sends documents to the master. For example, a simple CMS system that publishes new document to your Solr deployment. And then when the data came, it was indexed to master, but what happened when clients started to search the data? The replication was still not done, and what you get in result was old documents, right? Then the replication came, was kicked in, and everything back to normal. But for the short period of time, depending on your replication, on the polling interval, you had old data on your slaves. The one additional thing that was not convenient for the clients, at least from our experience, was sometimes the slaves had different poll intervals in order to not peak at the same time. And sometimes they tend to be a bit out of sync. So if you didn't use sticky sessions, if you had a load balancer, for example, here that distributed the queries among the slaves, and you didn't have sticky sessions, you could send the query to a single slave, then page, and oops, we have a different data view. That's not convenient at all. Sometimes, as in the real life, the data is too much for a single master just to handle. The indexing was slow, the queries were slow for a single slave. That's when you could introduce multiple masters. And of course, each master should have its own slaves, and the game begins again. Your application was needed to know to which Solr master the data should be put. You should have divided the data, put attention to it, and all that stuff. Of course, still the replication could be a problem. And if a single Solr master failed, some portion of your data could have been updated because they were living in a different part of your cluster. That's some technical difficulties you had to deal with when using Solr 3x and earlier ones. But after some time, okay, not the cloud yet, sorry. So how the query looked like in that multi-master deployment? It was similar to what we see today in the cloud, but still, your application needed to send a query with information which shard should be queried. For example, if you wanted to have a simple deployment with only three shards, we said that we want to have a shard 1, 2, and 3 be queried, and then the query was sent to a single shard. It distributed the queries to the other ones, gathered the results, and returned the response back, right? But what if you have multiple shards, multiple masters, and multiple shards? It was problematic because you had to know which shard to query. You had to distribute it evenly, so not to stress out a single server and things like that. And that's why SolrCloud comes into play. Before we go into specifics, let me give you some basic glossary about SolrCloud. So we have a cluster, right? Cluster consists of multiple nodes, at least one, but usually a single cloud cluster is only used for local development, at least usually. That's not always the case. The collection lives inside the cluster and is a logical view of your data, of all the small pieces living on each node. Then we have a shard, which is a Lucene index that lives on one of the shards. It's not distributed, it's a single shard. Each shard can be a reader or a replica. A leader shard is the one that the data gets to, and the data then is replicated to all its replicas. Just like with a master slave, we can imagine, with a simplified view, we can imagine that the leader shard is a master and the replicas are the slaves. But it doesn't work that way in cloud because they can switch roles. If a leader shard fails, the replica can take its role. And we have the overseer, which basically works as a housekeeper to pay attention to the cloud. You can find a full glossary on CWiki of Apache.org for Solr. The first thing when it comes to the cloud is a Zookeeper. It's an Apache project that is designated to take control over your cluster. We store configuration there. We store the cluster state there. It's updated in real time. And a quorum is required. What is a quorum? The cluster of Zookeeper servers, it's called an ensemble. An ensemble is one or more Zookeeper servers. In order to have a quorum, you need at least 50% plus one of Zookeeper servers available. Zookeeper needs a quorum to operate. So for example, if you have a single Zookeeper server, if it fails, your cluster will start to stop to receive data, they will be rejected, queries may not be working. If you have 3 servers in an ensemble, you are allowed to have a single Zookeeper server failed. If you have 5 Zookeeper servers, you can have 2 of them failed at the same time, and still your cluster will be operational. There is a simple configuration for Zookeeper. We can specify the client port, which is the client port on which Zookeeper will listen to our request. We have the data directory where the Zookeeper data will be stored. We have the tick time, which is a basic time unit in Zookeeper. In the example configuration shown, it's 2000 milliseconds. We have the init limit, which is the amount of tick messages in order to sync the Zookeeper servers to the leaders in an ensemble. And we have the sync limit, which defines how far beyond the leader can other servers be in Zookeeper. So basically, you take the number in, for example, the sync limit, multiply it by tick time, and we know that the servers can be maximum of 10 seconds after the leader. Also, if we want to specify the servers, we specify the Zookeeper servers, like here, the configuration size that we will have 3 Zookeepers, server 1, server 2, and server 3. What you need to remember about Zookeeper that it needs to be operational, and it's very rarely happening to have Zookeeper failed. However, you can adjust those to your, if your network, for example, latency is too high, you can adjust the tick time or sync limit or whenever you want in order to make it work. So where does Zookeeper play? What role does Zookeeper play when it comes to Solr? Each Solr node in the cluster, in SolrCloud, needs to point to Zookeeper ensemble. So whenever we start this new cluster, for example, we point it with the zk host parameter, and we specify which Zookeeper host it should connect to. On this picture, you see that each of the 4 SolrCloud nodes point to other Zookeeper servers, and 2 last ones are pointing to the same, because we only have 3 Zookeeper servers and 4 SolrCloud nodes. So if we want to create a collection in SolrCloud, because we don't create indices, we create collections, we run a simple command. First, we need to upload the configuration to Zookeeper. What we do is we use the zk client script provided with Solr. We use the appconfig command. We specify Zookeeper host. We specify the configuration directory that should be uploaded to Zookeeper, and we specify the configuration name. After that, the configuration will be uploaded and stored in Zookeeper, ready to be used by Solr. We can then use the collection API, which I'll talk about in a minute, to create a collection. What we do is we use the admin collections endpoint. We specify the action, which should equal to create. We specify the name of the collection we want to have. We specify the number of shards the collection should be divided to, and the replication factor, which tells us how many physical shards should be present, how many physical copies of each shard should be present. In that way, will create a collection of 2 shards because the replication factor is 1. After the command runs and it executes successfully, we have a view like this. Solr puts 2 shards on our cluster without any replicas at all, and the data flow looks quite simple. The documents are flying to the proper shards depending on their IDs. Solr, by default, calculates the so-called routing, which I'll talk about in a minute, takes the ID, calculates the hash, and sees to which shard the document should be, in which shard the document should be placed in. So it's the simple and very simple and logical view is like this, that the documents are distributed, one to the left and one to the right, one to the left and one to the right. So it's like this. However, of course, in order to have fault-tolerant clusters with high availability, we want replicas. We want to have some kind of copy of the data. So in order to do that, we use the same create command we've used earlier, but this time the replication factor is higher, 2. That will mean that each shard will have 2 physical copies. And the view of the cluster would be something like this, with the 2 shards and the replicas. Now let's look like how the data flow is. So if your application, once again, if your application sends a document, it will be again put in the correct shard based on its ID, if we use default routing. And then it's automatically replicated to its replica. When the replication is done, it is stored in the transaction log, and when it's done, your Solr replies with information that, okay, the document is stored, or a bulk of documents. The same happens when we get the second document. It's no matter to which, the one thing that's nice about cloud is it doesn't matter to which shard you send the data. Of course, it's more performant to choose to send the data to the leader, but it's not always possible because maybe you can't use the cloud server or something like that. You don't use Java in your application. So then Solr will automatically put the document in the correct shard, the correct leader shard, and again, it's going to be replicated properly to its replica, and the response will be returned. The indexing response. Now, how the querying works. A simple situation. We have a standard query, not grouped one, no use of field collapsing, and our application sends a query to whichever server we want in our cluster. The first stage is, because the querying is into phases, the first phase is sending the query to all the shards and ask only for the document top scoring document IDs and their scores. This information is returned to the Solr server, and then the documents are sorted on, if we sort by score, documents are sorted, and then the second phase comes in when Solr asks those documents that needs to be returned in order to build the response. Those are again another queries. The documents returned, and now we have all the information we need to build the response, and the response is returned as the results to the application. However, that changes when we use field collapsing, because with field collapsing, instead of 2 phases, we have 3 phases. First of all, so the aggregating node, let's call it like this, sends a request for top groups to each shard. The results are returned, sorted. Then the phase 2 kicks in that sends a query about top documents for each of the top scoring groups. They are returned, and finally the third part comes in where the relevant documents for each group is being queried for, the shards that contain them, and returned, and again results are returned to the application that sent the query. The usual question we get when we do consulting is how many shards and replicas we should use for our deployment. And the usual question we have is, it depends. Of course, it depends. It depends on how your data looks like and what your data growth will be and how much data you have currently. So sometimes it's enough to have 2 shards. Sometimes it's enough to have 10 shards. Sometimes you need way more. It also depends on the target performance, not only querying performance, but also the indexing throughput you want to achieve with your cloud. So if you want very high indexing throughput, a single shard or 2 shards or 3 shards may not be sufficient because the machine or I/O subsystem of the machine may just not be able to keep up. The same, if you want to split your shards across very high number of nodes, you need to have appropriate number of shards to do that. That's when the target node number comes in. There is a very simple equation that allows us to see the maximum number of nodes we can have for our deployment. It's the number of shards multiplied by number of replicas plus 1. So basically, if you have 3 shards and each shard have 1 replica, that means that you can have a maximum of 6 nodes having the data, because 3 replicas and each. So 3 shards, the leader shards, and 3 replicas means 6 physical shards. That's a simple equation to remember. However, what to pay, if you think of what you should go for when designing your index or the collection, is if you want to store more data, you need more shards. Of course, that's a very top view, high-level view of all, but it's usual like this. If you have more data, have more shards. If you want more queries and faster queries, have replicas, because they will be able to load divide the load among multiple nodes. I've mentioned custom routing. By default, when we use the num_shards parameter when creating the collection, we use the default routing. The default routing is, the routing algorithm is something that decides to which shard the data or the queries should be sent to. And if we have, by default, Solr takes the ID of the document, its identifier, calculates the hash, and checks which shards should be, which leader shard to send the data to, because in the cluster state JSON file in Zookeeper there is range of IDs that can be put in a given shard. However, sometimes default routing is not the best way to go for, and we can use a custom routing without specifying the num_shards parameter, and I'll show you how to do it and how to leverage it. For example, if we have multiple clients and we want to optimize our querying, so that during a query, we don't have to send the query to all the shards and get the data for a single client. But, for example, we would like to put the data of a single client in a single Lucene index, so in a single shard. What we can use, we can prefix the identifier of the document with something like, for example, user ID or username or something, and an exclamation mark. What Solr will do is it will put the documents with the same prefix to the same shard. Of course, the same leader shard, and then it will be replicated, but yeah, to the same leader shard. If another document come with a different, it will be put to a different shard. Of course, if you have hundreds of millions of clients, the data of some clients will live in the same shard, but Solr will decide to which. And during query, you can use it to run a query to it. For example, with the default routing used in Solr, the query, if you would set the query, it will hit all the shards in the cluster. If you have hundreds of shards, that may not be the best way to go for querying, because that takes time. Of course, your shard may be fast, but the network latency comes in, and the data needs to be gathered, processed, combined, and returned to the application. That's not always great. However, with custom routing, when we know where the data lives, or Solr knows that, we can do something like this. We can specify a query, and we can specify the route parameter with the prefix we've used for indexing, and then the query will hit only a single shard. Imagine again the situation with 100 shards. How much performance you gain when you only hit a single shard with it. So that's something to consider if you can structure your data like this, for example. That's something to go for. I don't have an exact numbers, but we've did some performance testing and we used to see for the data we could then big amount of data that, for example, it was at 10 to 100 times faster to hit a single shard, and that's normal if there are too many data to catch. Let's get back for a bit to the collection manipulation, because usually you won't end up with a single collection. You want to, and the collection manipulation commands that Solr exposes allow us to do different things. We can create collections, we can delete them, we can reload them, we can even split them if sometimes we see that the number of shards is not enough and reindexing is not an option. We can create aliases and delete them to, for example, have the timed collection we spoke about yesterday. Or we can even, when we are not using the default routing, we can even add new shards to the collections and delete them. For full reference, please refer to SolrCloud on Apache Wiki. The most used command is the collection creation, and it exposes a few parameters. The name, which is the name of the collection that should be created, the number of shards, which is the, as I said earlier, is the property that specifies the number of shards the index will be divided to, the replication factor, which specifies the physical amount of physical copies of each shard that will be created. However, there's one thing, in Solr 4.0, the replication factor was specifying not the exact amount of copies, but additional copies. So if you have num shards equal to 2 and the replication of 1, you had 2 shards and 1 replica for each shard. After Solr 4.0, so starting from 4.1, the replication factor parameter specifies the number of actual physical copies. So if you have num shards equals 2 and replication factor equal to 1, you get only 2 copies without any replicas. There is also a max shards per node parameter, which defaults to 1 and specifies the number of shards per collection that are allowed to be allocated to a single node. That's usually enough, and that's usually good to have a single shard. However, you may have enough power on your machines to serve more shards, and then when sometimes you would like to have more than a single shard per node, that's where you can specify how many shards should be placed. The create node set parameter is there to specify on which nodes Solr will create the collection. By default, Solr will try to spread the collection to all the nodes available, if that's possible. But sometimes we want to only create on few of the nodes, so that's when we can specify to the create node set command by only appending the IP addresses and the comma. So that's simple. And if the name of the collection is different from the configuration name is stored in Zookeeper, we need to provide the collection config name parameter to specify which configuration we want to use during collection creation. I love the split command. I really do, and that's why I always show how it can be useful. Imagine something like this. We have a single cluster with a single collection with only 2 shards. That's a cloud view in the Solr admin. And after some time, its indexing throughput drops and everything is going down slowly. And you finally say, okay, we need new shards, new leader shards, but the replication, but reindexing is not an option at all. And Solr comes with a split command, as I said, that allows us to split the shard into 2 shards. As Grant said earlier today, we will have also split by query sometime soon in Solr. But currently, Solr takes a single shard of the collection and split it to two. How it looks like, we specify the split shard command, we specify the collection, and we tell Solr which shard we want to divide. After this command runs, it can take a while, depending on how much data your shard contains, because basically Solr needs to read the whole data, the whole index, split it into two, rewrite the cluster state JSON, and delete the documents from the old collection, old shard of the collection. And after that is done, you would see something cloud view like this. We have this shard 1, which is still present. We have shard 2, which we didn't touch, and we have the shard 1.0 and 1.1, which should more or less contain the half of the documents the shard 1 contained. Then we can delete the first shard and forget about it, and we have a collection with 3 shards. We can then do this the same for the second shard, and we have a collection with 4 shards. We can add replicas then and distribute the shards among the cluster, because Solr doesn't do that by default, and kill the original shards, and we have it distributed. So it's nice. In addition to that, when dealing with data that is daily oriented, like the log files, we're usually interested in some especially newest data. So for example, we can use collection aliasing to not bother in the application with changing names. For example, we can create an alias called weekly when we store all the collections starting from today and back 6 days. So we'll have a view of a week. When we can use the name weekly to just query, and it will just look for like usual collection. We can also, if we don't need it, we can delete it. We can run the same command, but with the different collections parameter to adjust it to if a new day comes. That way, we don't have to really bother with what we query. If we need to query current day or the previous day, we just say, okay, we are querying weekly, or maybe daily, or maybe for newest. That depends on the use case, but we can do that with aliases provided by Solr. Caches. Caches play a big role in Solr, especially when mostly when querying. They are refreshed with index searcher. They are, of course, configurable, and they serve different purposes. We have a filter cache in Solr that is used to serve filter queries. For example, let's look at the following query. Lucene Revolution in Dublin, right? Is it a good query? It is. Is it optimal? No. Why? Because the city Dublin is a good candidate for filtering. For example, if we would change it to Q equals Lucene Revolution and filter query equals city Dublin, then the city Dublin would be put into the filter cache, and whenever new query came with the same filter, then it would be reused, and we would save I/O operations, CPU cycles, and all of that. So the query would be faster. In addition to that, sometimes we don't want to cache filter queries. Why? Because, for example, geolocation queries tend to be very heavy for cache. They change rapidly because your clients, for example, mobile ones, change their location very quickly, and you don't want to pollute the cache. That's why Solr allows us to specify cache equals false, and such entry won't be put into the filter cache. And in addition to that, we have something that's called cost in Solr. That's nice because sometimes you do filtering, for example, like the function range here, which filters the document based on the function query, summing to fields. However, I've seen function queries that were very long and very expensive to execute. And if the filter is not cached, and the cost is higher than 150, don't ask me why 150, I don't know, but 150, then the filter will be executed after all the other filters were. So we can imagine, because then you could save CPU cycles because the execution and all the calculations will be done only on the subset of the original returned documents by queries. It's nice, and it can speed up your queries a lot, especially when you're heavily using function queries to calculate things. I don't have an exact example currently, but we've seen, for example, string comparisons in filter queries, so that can be painful. We have a document cache in Solr, which stores the documents that can be reused. It's quite simple. And we have a query result cache that stores the information for queries. For example, again, the same query, and what will be stored in the filter cache is, apart from the query result cache, is apart from the filter query, all the other information, all the documents for the other part of the queries would. So in the query result cache, we would have results for a query with its sort and its result window. In addition to that, we can configure how many documents in advance we want to push into query result cache, because sometimes you experience paging and you want to prepare for paging. You want the next page or next 2 pages of your results to be served very quickly. Then you can adjust the query result window size. For example, you get only 10 documents for a query, and you can adjust the query result window size to 30. So the Solr will not only fetch 10 documents, but we will fetch 30 documents, and the next query will be faster. The query with the start 10 and again rows 10. It's like this. And of course, we have the query result max docs cached property in Solr config that we can use to say how many maximum documents we are allowed to store in the cache. When it comes to queries and filters, there is a warming mechanism in Solr, which basically allows us to pre-warm some internal structures like the caches to serve queries faster when the new segment arrives. I'll tell about segments in just a minute. There are 2 types of warmers in Solr. There is a new searcher and there is a first searcher. The new searcher is fired up every time a new segment, a new index searcher is opened. So, for example, when you commit or reopen the searcher, and the first searcher is fired up during startup. The thing is that the good candidates for warming up in that way are, for example, filters, or your sorting. If you know that you, for example, will be sorting on a string field or some date field or anything like that, you can put it into the warm-up, and when a new commit comes, it will be already, your queries will be already served, not cold, but from the warm index searcher. But you have to remember about use cold searcher set to false, because if you set it to true, then whenever a query comes, it will be used even if it's not warmed up. However, with use cold searcher false, Solr will not allow to use the cold searcher, the one that is warming up, and the old searcher will still be used to serve queries. Very important thing in Solr and Lucene is choosing the right directory for your deployment. The directory in Lucene is a interface, a logical thing, abstraction layer, that is used to interact with the index, writing and reading. So we have a few directories that we can use in Solr. It's the same in Lucene. Let's start not from the standard directory, but from the simple FS. It's a simple directory designed for single-threaded access. It will have issues with multiple threads. And the new IO FS uses the new IO package from Java, and it's quite nicely in Linux environment, however, has issues because of Java bugs. In Windows, we have the standard directory that is quite nice for not too many writes and not too many reads. If you don't have any memory issues, there is an mmap directory that is set to be used for the all the deployments actually currently. It's designed that way that it can reuse the caches of their operating system by using the mmap call. So the cache for the indices is the same in operating system and in Lucene. So that way, when operating system warms up something, it reads data to the memory, and then if you use the same from Lucene, you can, with the mmap directory, you can directly hit that operating system cache, and no additional seeks to the disk will be done. And there is an NRT caching directory that is packaging another directories and caches some data like the segment files to allow more efficient near real-time indexing and searching. And then there is a volatile RAM directory that just allows to store the data in RAM, but yeah, it's not designed for production purposes unless you have very small data and you can just reindex it whatever you want. In order to specify the directory, you can just set the directory factory in Solr config file, Solr XML, Solr config XML, sorry, file, and you'll be good to go. Sometimes when you have very big amount of data and your data changes rapidly, your faceting can't keep up. For example, faceting, because it needs to uninvert the index. That's why Lucene introduced DocValues, column-straight, column-oriented fields that are near real-time compatible. They are better cached than and better compressed than the field cache. They can store data outside of JVM heap, so you don't run out of memory when you use DocValues, for example, for faceting, or the maybe not run out of memory, but the probability of running out of memory is way less. And it can improve things for highly and rapidly changing indices. If you would like to use DocValues for your deployment, and you know that they are let me take a step back. They're basically a thing that allows you to have uninverted index stored in your inverted index. So they're totally different because usually you know how inverted index looks like. There is a term, there is a count, and of course a pointer to the document. However, this time we have a document and the values. In order to use DocValues, for example, for a field that's named categories, we can forget about indexing and storing that field at all. We just need to specify the DocValues equals true, and we will use DocValues, the column-straight fields. In addition to that, we can store DocValues on disk. However, we need to remember that it is still not fully backwards compatible. So if you have an index that stores DocValues on disk, you may run into issues when upgrading to a newer Lucene and Solr version. So that's one of the things you should remember if you want the DocValues to be stored on disk. Sometimes it's useful when you have a lot of data on in such fields. One of the things that comes with indexing throughput and with query throughput is the segment merges. Each small shard of our collection is divided into segments. Segment is a write once and read many times data structure that holds all your data and all your information about the documents. For example, imagine a situation like this. When you commit often, you end up having multiple segments because after commit and the flush, the segment is created and we can't update it. So after a certain amount of time, you would end up with multiple segments, and that would degrade your query performance because the more the segments, the slower the queries. So in order to fight that issue, Lucene has something called segment merging, and it works like this: that during a segment merge, the segments are divided into tiers on levels. Then, from each level, depending on the configuration of the merge policy and the merge factor, segments are chosen to be merged, and basically segments A and B in this case would be rewritten totally to a segment F C would be left alone because there is no other candidates to be merged. And again, D and E would be merged to G, which would result after the merge in 3 new segments instead of 5. We can control that process. We can set the merge policy, which I'll just talk about in a second. We can have a merge scheduler, which we control how the merges is done. We can specify the merge factor, and we, of course, can configure the merge policy itself. For example, this is the configuration of the merge policy called tiered merge policy. There are, in addition to that, there is a log merge policy and log bytes merge policy. We have 2 parameters configured here. Example ones, I wanted to show that max merge at once, that specify how many segments can be merged at once, and how many segments per tier, per level can be merged at once. In both cases, there are 10. There is a merge scheduler, the functionality that allows us to control how the merging is done. First of all, we have the default concurrent merge scheduler, which fires merging on the other thread, not the indexing thread. And we have the serial merge scheduler, which, not this thing, but here, going back to the merge scheduler, the serial merge scheduler that merges the segments in the calling thread, so the same thread that was used for indexing. In addition to that, we have the segments warmer. The Lucene has a functionality, a simple one, I think one implementation currently, but I suppose it will be, there will be new warmers soon. The merge segment warmer allows us to, basically Lucene will be able to merge, to warm up newly created, newly merged segments. So when Solr will use it, they will be already in the operating system cache, and all the Lucene internals will be ready for it to be as efficient as it can be. In addition to that, there is a merge factor, which basically specifies how many segments there are allowed to be in your index. For example, if you would have a merge factor of 10, like on the picture, and we would have a segment of 1,000 documents, so when 10 segments of 1,000 documents would be seen on the given level, then they would be merged together to a single segment of 10,000 documents. Then if the 10 segments of 10,000 documents came, it will be merged together for a single segment of 100,000 documents, and so on and so forth. We've talked about indexing, we talked a bit about querying, but what to pay attention to when you have high indexing throughput and you want to have it as high as possible? You need to adjust some things, probably. In general, you have to. There are a few properties and few things I would like to mention. There is a property called max indexing threads in Solr config, which specifies the maximum number of threads that are allowed to be used for an indexing process. There is a RAM buffer that allows us to define how much RAM we can use for buffering documents, and the same with the maximum buffered documents when we specify an amount of documents we may buffer. We should use bulks. Don't send documents one by one because it's not efficient, not only because of requests, but also about the network throughput, the parsing. We should use bulks. If you're using Java or any JVM-based language, Cloud Solr server is a way to go because it connects to your ensemble, the Zookeeper one, and it knows where your leader is for the given shard, so it can point the leaders to it can point the data to the correct leader. That's nice because you save network throughput that way and network latency. Of course, use autocommits and cut off unnecessary stuff from your configs. If you don't use fields but you just copy them because they were in the configuration, cut it off. Cut off unnecessary calculations like the norms if you don't need it, and omit term frequencies and positions for some fields. Maybe you don't need it. It will all increase your throughput, at least in the view of a single machine. But that goes and that scales So if you adjust your single machine and then have the configuration to all, that your indexing throughput will be higher. There is a thing in Solr, in addition to all that I've talked about, called a TransactionLog. TransactionLog is the new thing from 4.0 that ensures updates durability. It also, because whenever a document comes to Solr, it is not directly written to the index. It's first written to the transaction log, so you don't lose it in case of something happens, something bad happens. It also allows a peer recovery mechanism. So if your replica and leader shard get out of sync, you can use the Solr will use TransactionLog to replay the few of the newest documents. The maximum it's 100 of the newest documents, and the full replication won't have to kick in, because full replication needs to download the index files, and that's not always a good thing to do. And of course, it allows us to use a performant real-time get to get the documents that were not yet indexed and they were only written in the transaction log. We can configure the transaction log by specifying the update log property. It's by default, it exists by default in Solr config provided with Solr from 4.0, and of course the real-time get handler that you can get documents from transaction log. What about autocommits? I've told that you should use autocommits. There are two autocommits right now in Solr, starting from 4.0. 4.0? Yeah. There is a soft autocommit and hard autocommit. It's all about data visibility and data durability. The hard autocommits are there to ensure that the data is flushed to disk. However, and it's all about that. It can also refresh the index, but we'll talk about it. And excuse me. And there is a soft autocommit that is only there to ensure visibility, so to refresh your index searcher. In order to define autocommit, we have this section in the update handler configure. Update handler configuration in Solr config. We can specify the maximum time, the maximum documents before autocommit happens. And there is one thing that we usually use when dealing with soft and hard autocommits. And in a hard autocommit, we specify that we don't want to open index searcher. Why? Because hard autocommit should be only about data durability. So we don't care if the new index searcher is open. Hard autocommit is a bit costly when it comes to I/O, and that's why we don't want to open the searcher with it. However, with soft autocommit is there to reopen the searcher and refresh the data. Let me show you how it is. I did a small performance testing, the indexing performance testing. And what I did, the first test was with the autocommit set, the hard one, set to 10 documents, and with reopening the searcher. What we get in results is believe me, it's about 3,000 requests per second and about 3 milliseconds and a bit above, a bit below of latency for each. So it was done on a almost empty index with an SSC drive and quite nice PC. So indexing throughput is nice. But now, when we turned off autocommit opening searcher and we increased the maximum documents allowed to be stored before the hard autocommit happens, but still we've opened the searcher in the same time, the latency dropped below 2 milliseconds. You can see that it dropped, and the amount of requests is higher than 4K, even for 5K, depending on how the merging was done in the background. So you can see the difference when you use autocommit and soft autocommit. This in general, if you're indexing constantly, you want the data to be visible as soon as possible, the soft autocommit will be set, for example, to 1 second, 10 seconds, depending on the hardware you have and what you can afford. And the hard autocommit will be higher, for example, 1 minute or something like that. That depends. You should do the testing and see how it works out for you. Okay. The other thing that was introduced in Lucene 4.0 is so-called flexible indexing. What flexible indexing is it allows us to define and to alter the way the data is written to the index. Basically, it allows us to define how postings are written to the index. Postings are docs, their position, and payloads. There are different postings formats available that serves different purposes. So, excuse me. Let's start from the Bloom posting format. It's designed that way that it has a Bloom filter and allows for very fast and efficient way to see if a document is present in a given segment. So if you do a lot of seek for documents, then it may help you because Solr will know, and it's more a Lucene level thing, but let's call it Solr will know if the document exists in a given segment. In addition to that, we have a pulsing codec, so-called codec, which allows us to efficiently index fields that have many unique values, the high cardinality fields. We have a direct codec, which stores inlines some information into the term dictionary. So one less disk seek needs to be done when retrieving a term. Because some information is already inlined in the term dictionary. And we have a memory which allows us to store some information, the postings information in memory, actually read it from a disk, store it in memory, so it's so Solr allows us to get it very fast. It's all on internal level, but simply, for example, for ID fields that has many unique values because you have one unique value per document, right? And if you have multiple documents, the pulsing codec can be a very nice speed up for retrieving documents by ID. There is also a simple text codec. You don't use it in production, but you can see what is written actually by Lucene in the index. It's just a plain text that is written to a files. It's nice to see if you want to experiment with those. In order to play with codecs, we need a codec factory defined. A simple schema codec factory will do, and its implementation is already included in Solr config. And in order to define fields that way, of course, we have a field definition that will use a type string pulsing, and for the string pulsing field type, we use a posting format called pulsing for 1, for example, and that's how it goes. And Lucene will use it during indexing. Last thing I wanted to talk about, it's an hour already. Last thing I wanted to talk about is monitoring. I promise, not too much. I always tell that because we have numerous clients asking for this. Really, you should pay attention to your cloud, because things work usually, but they tend to break also. So if something is broken, you need to know what causes the outrage. You don't want to dig into stuff when the clients are hitting your phone line and asking, why it is not working? Why? I need it to be working. That's why monitoring comes in. You need to pay attention to cluster state. What's the health of the cluster? If all of shards are healthy and stuff like that. You need nodes utilization information. If your nodes are not stretched out too much, if the queries and indexing is distributed evenly among the nodes, more or less, of course, evenly, but you should see the same pattern. You should see memory usage to avoid out-of-memory problems and adjust your memory pools the way that everything works before something bad happens. You need to pay attention to caches utilization because sometimes you may not need caching. If you have querying, if you have indexing logs, for example, then caches may not be a good option at all because they will be refreshed every second, for example, if you want to do that with AutoSoft Commit. And that's not a good stuff to do because the caches will have to be warmed up, copied, and stuff like that, and that costs CPU. You need to monitor your query response time, at least in most applications that serves data, like e-commerce sites or anything like that, because you don't want your clients or your clients to be waiting too much for the results. People are used to Google, Bing, and they are just wanting to have the results, the relevant results, as soon as possible. So that means right now or a minute before. In addition to that, you have to pay, if you're using caches, you have to pay attention to the warm-up times because too much warming up can result in Solr behaving not the way you would like it to be. And of course, the garbage collector work, which is a JVM thingy, but you should pay attention to it because you don't want the stop the word events to happen because your Solr will stop to respond. Fortunately, JVM is getting better and better, so that's nice. However, you should avoid monitoring like on this picture. It's a real picture from my PC some time ago when I was monitoring a few servers of our clients. And you can see a few putty terminal connections. No, don't do that. It's not good. We can use JVM for monitoring. We just start Solr with a single parameter. We connect, for example, with JConsole provided with the JVM, and we can see the threads. We can see the memory usage. Of course, we can see the threading and the memory tabs. We can also see all the beans exposed by Solr. But the way it's worked, it's not persistent, so you can't see what happened 1 hour ago when you were asleep and the cluster failed. So that's really, in production, that's not an option. You can observe it in real time, but no one observes their clusters 24/7, at least not manually. Of course, you can use the administration panel provided with 4.0. It's very nice. It provides basic information about your cloud, about nodes in your cloud. You can see the memory usage, index statistics, JVM memory, file descriptors. You can also see the beans, the mbeans, just like with JMX, exposed like the caches, the update handler statistics, the request handler statistics. But usually you want to go with the monitoring solution, not only SPM like we provide, but with monitoring solution that can persist your data for a period of time because you want to see what was happening back then. You can see it's SPM. If you want to play around with it, come to our booth. You can see how it works on the real data. There are other monitoring tools available for usage. There is an open source Ganglia. There is our competition's New Relic. There is an ObsView application. They're all nice, and they all play that role. Depends on what you actually want to pay attention to. We provide the services to monitor, for example, Solr that are designed to work with Solr. And we are hiring as usual. I wanted to put some wrap it up slide today, but to be honest, I didn't know what to wrap up because of the information. So if you want to catch me up, there's a my Twitter account, my mail, Sematext Twitter, and our webpage and the blog. And of course, we are here at the booth, so you can catch us up, talk to us, ask questions. We are there for you. And if you want to try SPM, it's free for 30 days after you register, but you can use the discount after to get a 20% discount on the normal prices. Thank you very much. And do you have questions? Yes, please.
So I understand that Solr Day
Wait, I'll come to you. I don't see Mike. Yeah, the question was if in SolrCloud we can have different collections with different configurations, right? Yes, it's possible.
Different schema and different.
Yes, it's possible. You can upload multiple configurations to Zookeeper. Just provide a different name, and then during collection creation, you just use the configuration name, and Solr will use the proper configuration. So once again, thank you very much for coming here. I hope you enjoyed it. Bye-bye. Enjoy the rest of the conference.